So, this is lecture number 33 of the course on fundamentals of transport processes. Welcome. We were discussing solutions of the diffusion equation in the last class. So, just to recap where we were, we had initially derived conservation equations for mass and energy conservation in different coordinate systems, in a spherical, cylindrical as well as a Cartesian coordinate system. And all of these had a similar form. Okay. They all had the form dc by dt plus the divergence of u c is equal to d del square c plus the source or sink of energy. Okay. So, this was the form of the conservation equations both for mass and energy. Only in the case of energy conservation, you substitute the temperature instead of the concentration and the thermal diffusion coefficient instead of the mass diffusion coefficient. So, this is the common form of the diffusion equation. This is commonly called as the convection diffusion. Equation. The left side of the equation contains first a time derivative, the rate of change of mass within a differential volume with respect to time, divided by the volume itself. So, C is a concentration. And then there is the convective term, the rate of transport of mass due to the mean fluid flow. This takes place because the mean fluid velocity u, which has different components in different coordinate systems. So, this is transport along the direction of the mean flow. And then there is this diffusion term, which is the transport of mass due to the fluctuating velocity of the molecules. Recall that when we derived this term, we had assumed that the diffusion coefficient is independent of position. Okay. So, that is an assumption that goes into all of these equations. And then there could be a source or sink of energy depending upon whether mass is produced or consumed in a reaction due to reactions. Similarly, energy could be produced or consumed either due to exothermic or endothermic reactions or due to phase change or various other reasons. So, this is the general form of the convection diffusion equation. The left hand side contains the rate of change and the convective term, while there is the diffusion term on the right hand side. And if I scale my coordinates by a characteristic length and a characteristic velocity, so if I define the length x vector is equal to the characteristic length times x star, where x star is a dimensionless coordinate, u is equal to capital U times a dimensionless velocity. Okay. In the case of flow around a particle, the length would be the particle diameter and u would be the free stream velocity. In the case of flow past surfaces or through channels and tubes, L would be the radius of the tube or the width of the channel, u would be either the maximum or the average velocity. Okay. And one can define the dimensionless time quite easily. This has to be u by L times t. If I put all these into the conservation equation, okay, along with a dimensionless concentration, okay, where C naught is some characteristic concentration, okay, then my equation becomes P e times partial C by partial t plus del dot u c is equal to del square C plus the source, okay, where the Peckley number is equal to u L by t. Okay. It gives you the ratio of convection and diffusion. Dimensionally, the diffusion coefficient has dimensions of length square per unit time, and therefore, this is a dimensionless number. The velocity times the length divided by the diffusion coefficient. In the limit where the Peckley number is small compared to 1, okay, the equation just becomes d del square c plus s is equal to 0. Okay. So, in the limit where the Peckley number is small compared to 1, we have the diffusion equation as d times the Laplacian of the concentration field plus the source or sink is equal to 0. And in the limit of low Peckley number, diffusion dominated transport, we were examining strategies to solve the equation of the form the Laplacian of the concentration is equal to 0. We already saw one way to do this, and that is by separation of variables. If you recall, when we solved the problem of flow in a cubic in a Cartesian coordinate system, for the flow in a Cartesian coordinate system, okay, we derived the equations for u dot grad c is equal to d del square c, and then we had solved the problem of flow of heat transfer in a cube. Okay. This cube had different temperatures on the different surfaces, and we used the method of separation of variables to separate the temperature dependence into two components, one of a function only of x, the other only a function of y. Okay. And we got basis functions and eigenvalues in the form of sine and cosine functions in the coordinate where there were homogeneous boundary conditions. Okay. So, in this particular case, in the y coordinate there were homogeneous boundary conditions, and we got basis functions in the form of sine functions in that direction, exponentials in the x direction where there were inhomogeneous boundary conditions, and we saw how to construct a solution as a sum of these basis functions which are all orthogonal to each other. And then we did the same thing for the time dependent problem. In this case, one has to be careful, because when one solves this in 3 independent coordinates, one has to ensure that there are homogeneous boundary conditions in 2 out of the 3, and there is inhomogeneous boundary conditions only in 1. In this particular case, we had defined the transient temperature as the difference between the actual temperature and the steady state temperature. And once we did that, we got homogeneous spatial boundary conditions for the transient temperature field. There was an inhomogeneity only in time, and due to that reason we got exponential dependence in time and sine and cosine functions in both the spatial coordinates. I showed you how to do that for a spherical coordinate system. Okay. In this particular case, we have r as the distance from the origin, theta is the angle made by the radius vector with respect to the z axis, and phi is the angle made by the projection with respect to the x axis. So, we have x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. And by defining the surfaces of a differential volume, okay, we have to choose the surfaces to be of constant coordinate, 2 surfaces in the r direction, 2 in the theta direction, and 2 in the phi direction. And by defining these surfaces of constant coordinate, we derived the differential equation, okay, for the concentration field. Once again, it had exactly the same form as that for the Cartesian coordinate system, except that these operators, the divergence on the left, the Laplacian on the right, are different in a spherical coordinate system. The reason is because the surfaces of constant coordinate are curved surfaces, and the unit vectors perpendicular to these change with position. Okay, so, we had defined the divergence in the Laplacian coordinates in this coordinate system as well. And I briefly showed you the equations in the cylindrical coordinate system. Okay, they have a similar form once again, and after that we had come down to this convection diffusion equation, okay, and taken the limit of Peclet number becoming small to get to the diffusion equation. Now, we solved the diffusion equation in a spherical coordinate system by separation of variables. Okay. In the phi direction, we got eigenvalues, okay, integer eigenvalues in the phi direction, okay, from the requirement that when you go around by an angle of 2 pi, you come back to the same physical location in space. Therefore, in the sine and cosine solutions along the phi coordinate, the coefficient has to be an integer, because without that you will not get back the same value when you go around by an angle 2 pi. Then we looked at the theta equation, and I showed you that the solutions are the equation that results for the theta coordinate is in the form of what is called a Legendre equation, okay, and the solutions for these are what are called Legendre polynomials. Okay. These solutions turn out to be finite only if the constant in the theta equation is of the form n into n plus 1. Otherwise, the solutions become infinite at theta is equal to 0 or at theta is equal to pi. So, you get discrete eigenvalues in the theta direction as well, okay, from the requirement that the solution has to be finite both at theta is equal to 0 and theta is equal to pi. So, combining the r and theta directions, we get solutions in the form of what are called spherical harmonics. Okay. These are products of p and m of cos theta, Legendre polynomials, and sine or cosine of phi. Okay. These have their own orthogonality relations which can be used in order to determine coefficients in the differential equation. And then finally, we looked at the radial part of the equation, and this just has two sets of harmonics, a growing harmonic proportional to r power n in the limit as r becomes large, and a decaying component which decreases r power minus of n plus 1. So, it goes as 1 over r power n plus 1. Okay. And combining these, as you can see in the red at the bottom, we have the final solution in terms of spherical harmonics, and the r dependence is in the terms of r power n and 1 over r power n plus 1. Okay. And I showed you how these orthogonality relations can be used for the specific case of the effective conductivity of a composite. We looked at this only in the dilute limit, where the number of particles is small, such that the temperature field around one particle does not affect the temperature around another particle. So, this effectively reduced the problem to finding out the flux within a particle, okay, which is placed in a temperature field which has a linear temperature gradient far from the particle. Okay. And we solved this problem using the spherical harmonic expansion, and I showed you that since the temperature far away from the particle is proportional to T prime times P1 of cos theta, okay, the temperature far away is equal to T prime times P1 of cos theta. That means that the only solutions that which are non-zero are those proportional to P1 of cos theta itself, because all of the spherical harmonic functions are all orthogonal to each other. Therefore, if the forcing is of the form P1 of cos theta, the solution will also have that exact same symmetry. Okay. And using that condition, quite simply, we managed to get the coefficients in the equation, and from that find out the effective conductivity of the composite. Okay. Only for n is equal to 1 will you get non-zero solutions, because there is this inhomogeneous term in the equation. For all other coefficients, there is no inhomogeneous term. Two linear equations, two unknowns, both of them homogeneous. The only solution is for both of these coefficients to be 0, a result of the orthogonality condition, that all the spherical harmonics are all orthogonal to each other. Therefore, the symmetry of the solution is the same as the symmetry of the forcing that was applied, in this case proportional to P1 of cos theta far from the sphere. And from that we managed to get the effective conductivity of the composite in the dilute limit. And I had explained to you the symmetries that arise from the spherical harmonic expansions, okay, briefly. And then we went on to looking at a point source, a delta function source. I had defined for you the point source in the previous lecture. Okay. A delta function is defined as a function which is 0. Okay, delta of x is defined as to be 0 for x not equal to 0. Okay. The area under the curve of the delta function is equal to 1, and if you multiply the delta function by any function g and integrate over all over the x axis from minus infinity to infinity, you will get g of 0. Okay. This delta function is the limiting case of a function such as this. It has a value 1 over h when x is between minus h by 2 and plus h by 2, okay. 0 otherwise. So, in the limit as h goes to 0, the height increases, the width decreases to 0, and you get a delta function which is 0 for all x not equal to 0, and it is non-zero only at x is equal to 0, in such a way that the area under the curve has to be equal to 1. This is not a unique choice. There are other functions as well which can be reduced to delta functions in the limit as h goes to 0, but for the moment we will restrict ourselves to just this form of the delta function. With this form of the delta function, I showed you that the integral, okay, of delta of x times g of x, okay, from minus infinity to infinity is equal to the value of the function at 0 itself. Okay. Similarly, delta of x minus x naught times g of x has to be delta at the location x naught. You are just shifting the origin to x naught. In that case, delta function is located at the location x naught. As defined here, integral minus infinity to infinity of dx times delta of x has to be equal to 1. That means that delta function has dimensions of 1 over length in this case. In a similar manner, one can define a two-dimensional delta function. Okay. I had in fact drawn it for you in the previous class. X y axis on the plane, f of x is in the perpendicular to the x and y directions, and this delta function is defined such that f of x y is equal to 1 over h square for minus h by 2 less than x less than h by 2 and minus h by 2 less than y less than h by 2, and it is equal to 0 otherwise. Okay. And the integral of the delta function over x and y, integral dx dy f of x y has to be equal to 1. In the limit as h goes to 0, one gets the delta function f of x y is equal to delta of x y. Okay. So, this two-dimensional delta function has the property that the integral of delta of x y over x and y from minus infinity to plus infinity is equal to 1. Delta is equal to 0 for when x is not equal to 0 or y is not equal to 0. It is non-zero only when x is equal to 0 and y is equal to 0. And the integral minus infinity to infinity of dx dy delta of x y g of x y is equal to g of 0 0. So, basically this delta function picks out the value of the function g exactly at 0 0, okay, at the location 0 0. So, delta of x minus x naught y minus y naught. Okay, so, this the straight extension of this is minus infinity to infinity. This will be equal to g of x naught y naught. Okay. just shifting the origin to the location x naught and y naught. In a similar manner, the 3-dimensional delta function is defined as 1 over h cubed for x between minus h by 2 and h by 2 and y between minus h by 2 and h by 2 and z between minus h by 2 and h by 2 equal to 0 otherwise. Limit as h goes to 0, you get the 3-dimensional delta function. Okay. And this has the properties integral over the entire volume of delta of x y z is equal to 1, and it is equal to 0 for x not equal to 0 or y not equal to 0 or z not equal to 0. And if you take the delta function and multiply it by any other function and integrate over the entire volume, it will pick out the value of that function at the origin. Okay. In the remainder of these lectures, I will use the shorthand notation x vector for the 3 spatial coordinates x, y and z, and dv for dx, dy, dz, and we will integrate over the entire volume. Note that as defined here, delta function in 3 dimensions has dimensions of 1 over volume, because when I take the delta function multiplied by the volume and integrate, I get a result that is dimensionless. Therefore, the delta function has dimensions of 1 over volume. Okay. And we had looked at how to use the delta function to get solutions of the diffusion equation. For a point source which is emitting heat per unit time equal to Q, the solution for the temperature is equal to Q by 4 pi k r. Okay. So, that is the solution for the temperature field due to this point source located at the origin. I showed you that this temperature field is also obtained using a diffusion equation of this form. K del square T plus Q delta of x is equal to 0. Okay. Since delta is non-zero only at x is equal to 0, for everywhere that x is not equal to 0, I can solve the Laplace equation K del square T is equal to 0, and I will get the temperature as some constant divided by R. This constant is determined from the condition that the total heat coming out of the point source has to be Q. Okay. So, if I take an equation of the type K del square T is equal to minus Q delta of x, okay, and then integrate it over a small volume around this point source, okay, the integral over the volume of integral of K del square T over the volume is equal to minus Q, okay, because integral of the delta function just gives me 1, where Q as defined is the heat generated per unit time from the source. The first term can be simplified a little. Integral over the volume of K del square T is equal to integral over the surface surrounding this volume of the unit normal dotted with K grad T, okay, where gradient of T is in the radial direction, because T is only a function of radius. Okay. So, if I take K grad T and multiply it by the unit normal, okay, and integrate it over any surface, okay, the gradient of the temperature goes as 1 over r square. It decreases as 1 over r square. The surface area increases proportional to r square. So, if I take K grad T and integrate it over the surface, I will just get something that is independent of radius, turns out to be equal to minus 4 pi k a. And from that I get the constant A is equal to Q by 4 pi k. Okay. So, therefore, this is the solution for the point source. Okay. The solution for the equation of this kind, minus K del square T, K del square T plus the source of energy is equal to 0. The solution for that is T is equal to Q by 4 pi k r. At the end of the last lecture, we were discussing that if you have one point source, the temperature is Q1 by 4 pi k times the distance between the source and the observation point. X1 in this case is the point at which the source is located. X is the point at which you are taking the temperature. So, that is the observation point. So, the temperature field due to a source is equal to the energy generated per unit time divided by 4 pi k times the distance between the source point and the observation point. If I had two sources, I can write down the temperature fields individually due to each of these sources and add them up to get the temperature field due to the two sources. Okay, so, this is the temperature field due to two sources together. I just take the temperatures due to the individual sources and add them up. Okay, so, this is a procedure known as linear superposition. The equation for the temperature field is linear. Del square T is equal to source or sink. It is linear in the temperature. Okay. And therefore, if I have two sources, I can define the temperature fields due to each of those sources individually and add them up. One has to be careful while doing linear superposition in that when one adds up the temperatures, the boundary conditions, the configuration has to be kept a constant. I explained this in the last lecture, but it is worth explaining again. If, for example, I were solving the temperature due to two spherical particles, one of them was generating heat Q1, the other was generating heat Q2. I cannot write it as the sum of two problems, where in the first problem I have only one particle present and the second problem I have only the second particle present. This is not correct because the boundaries between the original problem and the two sub problems are different. In the original problem, there are boundaries on both the spherical particles. In the two sub problems, there is only one spherical particle each. So, this is not a correct way to do linear superposition. The correct way to do it is to divide it into two sub problems, each of which has both the spheres present. In one problem, I can have only one of the spheres emitting energy. In the second problem, I can have only the second sphere emitting energy. Therefore, in both of these problems, the boundaries are exactly the same as in the original problem. The source or sink of energy is different, but those can be added up to give the original problem. Okay. So, this kind of linear superposition is possible, so long as you do not change the boundaries in the sub problem. Okay. And that is why the concept of a source, a point source, is such a valuable one, because a point source has no dimension, it has no size. Therefore, whether I have a point in the field or not is not really important. What comes out of that point is important. Okay. So, in this case, I am able to superpose two problems in which there is one point source in one case, the other one in the other case. Since the point has 0 volume anyway, okay, it does not matter if a second point is present, so long if it is not emitting energy, it does not enter into the problem. And that is why it is far more useful to use point sources in order to represent continuous fields. So, that is the big advantage of point sources. I can remove and add sources and still be able to use linear superposition, whereas for finite size particles it is not possible to do that. Yeah. And briefly, at the end of the previous lecture, I had said that if you had a distributed source, I can still divide it into a large number of point sources. Let us say I have a distributed source in which the heat generated is Q per unit volume per unit time. This distributed source can be divided into a large number of smaller volumes in a space filling manner, in such a way that each volume has its source at the center of that volume. In the limit, as the volume goes to 0, this will reduce to the distributed source. So, I have heat generated per unit time in each volume as the heat as the Q, which is the heat per unit volume per unit time, times the volume itself, okay, for each of these sub volumes. So, the temperature at the observation point, okay, the temperature at the observation point due to each of these sub volumes is Q times delta V divided by 4 pi k into x minus the source point, okay, the distance between the source and the observation point. So, to get the total temperature, you just add up all of these individual source points, okay, to get the total temperature. In the limit as delta V goes to 0, you can convert this from a summation to an integral over the entire volume. So, temperature at the location x is equal to integral dV prime q of x prime divided by x minus x prime, the modulus, that is the distance between the source and observation point. Note that x prime is the source point, it is the location at which the source is, and x is the observation point. So, I am calculating the temperature T at the location x, and it is a function of the where the source is located and how much heat is coming out from the source, okay, and the distance between the source and the observation point. So, how do we use this for solving actual problems? Okay, so, let us just solve an example. Let us say that I have a heated wire. I have a heated wire, okay, and it has a distance 2L. The length of the wire is 2L, and it goes from minus L less than or equal to y less than or equal to L. Okay. So, this is a wire that is emitting heat which is Q per unit length per unit time. Okay. So, this is the heat that is being emitted by this wire. Okay. So, and at any location x, okay, one would like to find out what is the temperature, okay, due to the heat emitted by this wire. Okay. So, one would like to find out what is the temperature field due to this wire. So, this is the source, okay, the source of heat is this wire. It is a thin wire along the y axis, okay, along the y axis, okay, and it is emitting heat Q per unit length per unit time. Okay. That means the source, okay, it is non-zero only when x is equal to 0 and z is equal to 0 and y is between minus L by 2 and plus L by 2. Okay. So, this is equal to Q. Okay. Note that in my differential equation, okay, K del square T plus S E is equal to 0. Okay. This source has dimensions of heat generated per unit volume per unit time. Okay. This wire is emitting heat Q per unit length. Okay. So, the heat emitted per unit volume per unit time, note it is non-zero only when x is equal to 0 and z is equal to 0. It is 0 otherwise, okay, it is 0 otherwise. So, this, okay, this Q is not equal to 0 only for x is equal to 0 and z is equal to 0, because it is a wire that is along the y axis, okay, and is equal to 0 otherwise. Okay. And I also require, okay, that integral dx integral dz as E of x. Okay, this integral dx integral dz times S E of x should give me the total heat coming out per unit length, okay, per unit time. Okay, so this has got to be equal to q. Now, what is the function that satisfies all of these properties? The function is 0 if x is not equal to 0 or z is not equal to 0. It is non-zero only when x is equal to 0 and z is equal to 0. Total integral of that over x and z has to be equal to q, which means that SE of x is equal to q times delta of x delta of z. Okay. So, this gives me the expression for the source in the equation. SE of x is equal to q times delta of x times delta of z, because this function is non-zero only when x is equal to 0 and z is equal to 0. Integral of this function over both x and z is going to give me q, okay, for minus L less than or equal to y less than or equal to L. Okay. So, in over the length of the wire, this source is non-zero, otherwise it is 0. So, I have framed the equation for the heat conduction as well as the source S in terms of the heat generated per unit length per unit time. I recall that SE has dimensions of energy per unit volume per unit time. Q as defined here has dimensions of energy per unit length per unit time. Okay. Q as defined here has dimensions of energy per unit length per unit time. Therefore, if I take q and multiply it by delta of x and delta of z, I get something with dimensions of energy per unit volume per unit time. Okay. Therefore, I have to solve now k del square t plus q delta of x delta of z is equal to 0. We already know what the solution to this equation is. The solution is t is equal to 1 by 4 pi k integral dv prime, okay, delta of x prime delta of z prime q by the distance. Okay. Let me just write this for completeness as t of x. So, x here is the observation point, x prime is the source point, vector x prime is the source point, vector x is the observation point. The source is q times delta of x times delta of z. That means that the temperature is 1 over 4 pi k integral over the volume dv prime delta of x prime times delta of z prime times q, that is the source s of x prime by x minus x prime. Okay. At a given location, in order to evaluate this, okay, I need to actually carry out the integral 1 over 4 pi k integral dx prime dy prime dz prime q times delta of x prime delta of z prime divided by the distance. The distance is square root of x minus x prime the whole square plus y minus y prime. So, that is the distance, the modulus, I am sorry, there is no square here, the modulus of x minus x prime, that is the distance, 1 over x minus x prime, which is square root of 1 over x minus x prime square plus y minus y prime square plus z minus z prime square. So, now how do we evaluate this function? we already know what the properties of the delta function are. Integral dx delta of x minus x prime delta of x g of x is equal to g of 0, the value of the function at x is equal to 0. Here I have two integrals with respect to the delta function. One is an integral over x prime of delta of x prime times some function. Okay. The second function is some function of x prime. So, the integral is just going to be equal to the value of that function at x prime is equal to 0. Okay. So, using this property I can rewrite the temperature x integral dx prime times delta of x prime divided by some function of x prime. This is just going to be equal to integral the value of this function at x prime is equal to 0. So, this is square root of x square plus okay. Now, once again I have an integral over z of delta function times this other thing, okay, the delta function times this other whole thing. So, this once again I can write this as 1 over 4 pi k integral dy prime q by square root of x square plus y minus y prime. Okay. So, because of these two delta functions, the final equation for the temperature has been reduced to just an integral over the y coordinate alone. Okay. This can further be simplified. Note that there is a source of energy only when y is between minus L and plus L. Okay. There is a source of energy only when y is between minus L and plus L. Okay. Therefore, I can write this as q by 4 pi k integral between minus L and L dy prime 1 over root of x square plus y minus y prime plus z square. So, this integral can actually be evaluated analytically. Okay, this integral can actually be evaluated analytically. The final result that you get when you evaluate this integral analytically is that t of x is equal to q by 4 pi k log of L plus y plus square root of r square plus L plus y the whole square by the r in this solution is the radial coordinate in a cylindrical coordinate system in which the axis is the y axis. Okay. It comes out naturally in this form. The reason is because if I go back to the original problem, this problem there is a wire in the y direction, okay, along the y axis. Therefore, as you go around the y axis, okay, in the xz plane there is no change. Therefore, it will be more convenient to analyze this in a cylindrical coordinate system in which y is the axial direction and r is the distance from this axis and theta is the angle around. Because there is no variation in the theta direction as you go around this, okay, therefore, you get the solution to be symmetric with respect to x and z. Okay. The final solution ends up of the form square root of x square plus z square. Okay. So, this of course gives us the analytical solution. The question is what physically does this mean? Okay. So, as usual, let us take two limiting cases. Okay. To simplify the problem, I will assume for the moment that we are along the x z plane. Okay. Y is equal to 0, okay, and therefore, t is equal to q by 4 pi k log of L plus root of r square plus L square okay. So, I have my wire along the y coordinate and I am along the x z plane. So, I am taking a distance, an observation point that is somewhere along this x z plane. Okay. And for this observation point, the distance from the origin is the radius r. Okay. And of course, the solution is symmetric with respect to r. It depends only upon the distance from the axis. Okay. So, this is the solution along the x z plane. One can consider two limiting cases here. Okay. The first case is when r is large compared to L. Okay. This wire has thickness 2L. So, when r is large compared to L, that means that the distance from the origin is large compared to the length of the wire itself. Okay. In that case, I can do an expansion in small L by r. I can rewrite this equation as t is equal to q by 4 pi k log of L by r plus square root of 1 plus L by r the whole square by minus L by r plus square root of 1 plus L by r the whole square. And then expand the log function in the small parameter L by r. Okay. And if you do that expansion, the final result turns out to be equal to 2 q L by 4 pi k r, where r is the distance from the origin. Now, this looks exactly like the solution that we got for a point source, because this 2 q L, okay, you recall, for a point source that is generating q amount of heat per unit time, we got the solution as q by 4 pi k r. In this case, q is the amount of heat generated per unit length per unit time, and the temperature we are getting when the distance is far from when the distance from the source is large compared to the length of the source is 2 q L by 4 pi k r. The length was 2 L, the amount of heat generated per unit length was q, total amount of heat generated is 2 q times L. So, we are getting exactly the same solution that we would get for a point source, except that q in this case is the total amount of heat generated per unit time. And this is physically, the reason is because when we go sufficiently far from the source, okay, the distance is large compared to the length of the source. If you go sufficiently far, the source will always look like a point source. If you are sufficiently far away, we will not see the details, the detailed geometry of the source. It will appear to us to be just a point. Okay. and the solution that we get will just be equal to the solution due to the point source. Okay. So, this is just the leading order term in the expansion. There are higher terms, of course, we will see that in the next lecture, the dipole term, the quadrupole term, and so on. Okay. But this is just the leading term in the expansion, and physically this is because if the distance from the source is large compared to the characteristic dimension of the source, then it looks just like a point, and the solution that I get for the temperature field is exactly the same solution that I would have got for a point. So, physically that is what happens when the distance from the source is large compared to the characteristic dimension of the source. We can consider the opposite limit, r is small compared to L. Okay. So, in that case the actual distance from the source is small compared to the overall length of the source. Okay. If I take the distance from the source being small compared to the overall length of the source, in that case I can use an expansion in small r by L, okay, the other way. Okay. And if I take this equation, okay, and do the expansion in small r by L, I get T is equal to log of 1 plus square root of r by L square plus 1 by minus 1 plus square root of r by L square plus 1, okay, and 1 over 4. And if I expand out this log function in small r by L, then I will get the temperature Q by 4 pi k log of 4 L square by r square. Okay. Just expanding out this function in small r by L. Okay. And I can further write this as Q by 2 pi k to log of 2L minus log of r. So, when the distance from the wire is small compared to the length of the wire, I get a log function as the solution of the differential equation. Okay. The temperature decays logarithmically with distance. Okay. This, as we will see a little later, is also the solution for a point source in 2 dimensions. Okay. If I am sitting very close to the wire, okay, the distance from the wire is small compared to the length. It looks like the conduction from a wire of infinite length. Okay. If I am close to some long linear object, the distance of that object is large compared to my distance from that object. Okay, the length of that object is large compared to my distance from the object. It looks like an infinite object, okay, infinite line. So, this looks like an infinite line source in 3 dimensions or a point source in 2 dimensions in the xz plane. And in 2 dimensions, the solution for a point source is a logarithmic function. Okay. If you recall, we had solved the problem del square t is equal to 0 in 2 dimensions, okay, which in 2 dimensions is 1 over r d by dr of r dt by dr is equal to 0. The temperature turned out to be C1 log r plus C2. Okay. And if we write this in terms of the amount of heat coming out per unit time, per unit length along the line, this becomes equivalent to Q by 2 pi k log r plus some constant C2. Okay. So, this is the amount of heat generated due to a 2-dimensional source. Okay. As I said, this logarithmic function is not really, does not really indicate some problem with the formulation. In 2 dimensions, the solution for the Laplace equation is the fundamental solution is the log function itself. Okay. And of course, with the log function one cannot really satisfy the boundary conditions at infinity. At some point one has to recognize that the object is actually of finite length in order to find out what is the in order to match the temperature fields. Okay. In any case, so this log function is the solution of the equation, and if we are sufficiently close to the wire, okay, if the distance from the wire is small compared to the extent of the wire itself, this appears to me to be conduction from a wire of infinite length in 3 dimensions or a point source of energy in 2 dimensions. The solution for that is a logarithmic function. Okay. So, therefore, this example illustrates how one can use the method of delta functions in order to solve problems for objects of finite dimension. Okay. So, with this this is an illustrative example of the use of delta functions. It also turns out that the delta function solutions can be related to the spherical harmonic expansions that we studied when we did separation of variables in spherical coordinates. So, in the next lecture I will start with that. How does one relate these delta function solutions to the spherical harmonic expansions that we did when we looked at spherical coordinates, and then we will look at general methods of using the delta functions to actually solve problems in more complicated geometries. So, the delta functions have a physical meaning which is more than just an idealization for spherical systems. That is the reason why spherical coordinates are so important. We spent a lot of time on this, on both the delta function solutions as well as the solutions in terms of spherical harmonic expansions. And the reason is because these point sources can be used in various contexts, not specifically for a given problem, but in any problem that you have. If you can write down the source or sink in terms of delta functions, there is an easy way to formulate the solution. So, next lecture we will start on the relation between delta functions and the spherical harmonic expansions. We will see you then.